Last time we talked about motion in 2 dimensions and how to solve 2-dimensional motion problems. And we discussed 3 steps for solving 2-dimensional motion problems. Step 1, define your coordinate system. Step 2, break all your vectors into components. Step 3, use those components to solve 2 1-dimensional motion problems. We already know how to solve 1-dimensional motion problems, so it should be pretty straightforward from there. However, the example we did was a block sliding down a ramp, and that's not really a 2-dimensional motion problem because the block really is moving only in one direction. It's just a direction at an angle. Today, I want to discuss real 2-dimensional motion problems, quote-unquote real 2-dimensional motion problems. To do that, we're going to be talking about projectiles. So let's say I have a cannon, and I fire a cannonball. Cannonball goes off, and at various points it's following this parabolic trajectory. And we can do a motion diagram for that parabolic trajectory if we want. I could say, here's where the cannonball is initially, here it is at point 2, here it is at point 3. And as we did before, we can draw velocity vectors on that cannonball. That's velocity 1, that's velocity 2, and this is velocity 3. I'm not paying too much attention to the size of the velocity vectors just yet, so assume these are not to scale. Those are our velocity vectors. I have not yet drawn my acceleration vectors, so I'm going to need to do that. Now, we know from our work before that gravity always pulls you down. So if we ignore the force of air resistance, the only force is going to be the gravitational force, which is going to pull this object straight down. Now, when we were initially discussing acceleration, we said that the acceleration points in the direction of the curvature. And we did an example where we were moving at a constant velocity. This is a similar example, although we are obviously not moving at constant velocity because as gravity is pulling you down, you are going to accelerate in the downward direction. Which means that you're going to be slowing up as you're traveling up and then speeding up on the way down. So these velocities are not going to be the same at every point. Really should make this velocity vector a bit smaller. Because it's moving slower at the peak of its motion than it is right when it takes off or right before it lands. For that reason, well, for many reasons, the acceleration is not going to be perpendicular as we've drawn it, perpendicular to the motion as we've drawn it before when we were moving at constant velocity. We know the acceleration of gravity is always going to be 9.8 meters per second squared, straight down. Now that's still into the curvature because this is frowny face, it is curving down, but it's going to be straight down. It's not going to be perpendicular to the motion of the projectile. And that has some implications for us. 2 implications in particular. 1, G only affects motion in the vertical direction. I'm going to define the vertical direction to be the y direction. I'm going to say only affects motion in the y direction. Here's your coordinate system. Just put it up over here. G only affects motion in the y direction. So it only affects motion up and down. It doesn't affect motion at all in the horizontal or x direction. More generally, I'm going to give myself a little more room here. X and y motion, or components of motion if you prefer, do not affect each other. So the fact that this projectile is moving in the x direction doesn't at all affect the motion in the y direction. The up and down motion has no effect whatsoever on the horizontal motion. What that means is even though we're moving at an angle and we're traveling up and we're moving in a parabolic arc, g still points down to 9.8 meters per second squared. The y motion is still going to be like the one-dimensional free-fall problems that we dealt with last semester. Now that can be a little tricky to understand. It's a little tricky to conceptualize. So to deal with that, to help us understand that, we're going to look at a few demonstration videos to see exactly why and prove, or at least demonstrate, that the x and y motions are completely independent of each other. Here's our first test. We are going to consider a shotgun. Here's my shotgun. Here's your trigger, there's your gun. Here's a bullet being fired out of the shotgun gun with some high initial velocity. I fire that bullet. It comes down over here this way. And it lands some large distance away from the shotgun. That's the fired bullet. I also have here a second bullet that I just drop. I just let it go. No initial velocity for that bullet. Which of these two bullets, we have our dropped bullet over here and our fired bullet over here, which of those two bullets will hit the ground first? The dropped bullet or the fired bullet? To see the answer, we're going to look at this both using a demonstration and also mathematically. Now, unfortunately, I do not have the demonstration here because I don't have the equipment, and I'm pretty sure I would get in trouble for firing guns on campus. But we do have the ability to link to other videos, at least I'm told we are. So you should see a link somewhere around here that I've never done this before, so don't know if it's going to work. But you should see a link somewhere around here that you can click on to see the demonstration video. I'm just linking to a video from the Mythbusters that got posted on YouTube. So what I want you to do is pause this video, go see the YouTube link, and then come back here and we'll do it mathematically, okay? Pause. Unpause, okay. Looking at this mathematically, if you have followed the instructions, you should know that there is not a significant difference between when the drop time for the dropped bullet and the drop time for the bullet that is fired. Why is that? Right? This is assuming that there is not a significant amount of air resistance or some sort of upward wind force on either bullet. Why is that? Well, if I look at the dropped bullet, and I look at the equation for its motion in the y direction, which is all that matters for figuring out when it's going to land. If I look at the dropped bullet, we have that the final height, y final, equals the initial height, plus Vy initial, so it's initial y velocity times time, plus 1/2 the acceleration times time squared. I know that the final height is going to be 0 because it's hitting the ground, assuming I've defined the ground to be 0. I know the initial height, let's say we dropped it from a height of 1 meter. That's the same for both the fired bullet and the dropped bullet. Here's the interesting part. The initial y velocity, none of them had an initial y velocity. This guy had no initial velocity at all. the fired bullet had no initial y velocity, even though it had a really big x velocity. So this is 0. And in fact, this is 0 for both cases. The same thing is true for the acceleration. The acceleration is 9.8 meters per second squared. For both the fired bullet and the dropped bullet. So I've written this equation down for the dropped bullet. The only thing we don't know is t. And we can use that equation to solve for the time it's going to take. But since all of these parameters that I've put in for the dropped bullet are the same as for the fired bullet, this equation is going to work for both. It's going to work for both cases. So whatever value I find for t, it doesn't matter. I'm going to get the same value for the fired bullet and the dropped bullet. So in both cases, we are going to get the same time it takes to fall, whether I drop the bullet or fire the bullet. Again, this is assuming there's no wind currents or anything that are affecting one bullet more than the other. Our next demonstration is the ball and a cup demonstration. So I have here a ball, I have here a cup. But this is no ordinary cup. The cup has a launcher inside it, so that when I put the ball inside, I can give this cup a signal to launch the ball. It should launch it straight up. Let's just see if that's going to work. So the way it works is on the front of this cup there's a little photo gate. And if I block that photo gate off with just a sheet of paper, you can see, if I can get it in there. Oops, no, I'll get that later. The ball will be projected straight up. And using this apparatus, we're going to test kinematic motion in 2 dimensions. And I've got a little bit of a riddle for you. So let's say I have my ball in the cup. The cup fires the ball straight up. Okay? Well, then it should come straight down in the cup. But what's going to happen if I set the cart moving and then fire the ball out of the cup? So the cup is moving with some constant velocity v. It's moving in the direction to the right. And it's going to fire the ball, what would have been straight up if it weren't moving. But now it's going to be fired up, but since the cart is moving, the ball's going to be moving as well. So the ball's going to go up, the ball's going to come down. And we want to know, where is the ball going to land? We've got really 3 options here. The ball is either going to land right in the cup. It's going to go too far and land in front of the cup. Or it's not going to go far enough and it's going to land behind the cup. So those are our 3 options. Option 1, in front of the cup. Option 2, right in the cup. Option 3, behind the cup. Where is the ball going to land? All right, let's see what's going to happen. So why does the ball land in the cup? Well, let's look at the x component for 2 things. Let's look at the x component for the ball at various points along its motion, and the x component for the cup. Well, for the ball, I can write that its final position is equal to its initial position plus its initial velocity in the x direction. We're just looking at the x direction here. Plus 1/2 its acceleration in the x direction times time squared. That's just from our kinematics equation. And I'm looking for where the ball is, what is its x position at any given time. Well, let's just define our origin to be its initial position. So that would be 0. Its initial x velocity, well, initially it's moving with the cart. It doesn't have any x velocity other than what the cart has. So that's just the velocity of the cart. Its initial x acceleration, well, it doesn't have any x acceleration because its only acceleration is due to gravity, and gravity pulls in the y direction. Again, assuming the x direction is the horizontal direction and the y direction is the vertical direction. But the x motion for the ball is exactly the same as the x motion for the cart. The cart, if I want to know what the cart's final position is, well, it started in the same position that the ball was in, so its initial position would be 0. It is moving just with its own velocity, so the velocity of the cart, which holds the cup, is just v cart, same as up here, and it has no acceleration, because again, the only thing that could be accelerating us here is gravity. So assuming I've leveled the track, we should get no acceleration. So the x position of the ball and the x position of the cart and the cup should always be exactly the same. That means that anywhere the ball is, the cart and the cup should be directly underneath. So by the time the ball lands, it will land in the cup. The final demonstration we're going to consider is something called shoot the monkey. So we have here a hunter, and he is trying to shoot a tranquilizer dart into a monkey so that he can study the monkey for observation. The monkey's going to be fine, it's just going to be passed out for a little bit. But the monkey is going to be startled by the bang from the gun. So immediately, right as the hunter fires the gun, the monkey will let go because he's startled. So you want to shoot a tranquilizer dart into this monkey as it's falling down. And we have to remember that the monkey is going to be accelerating downward at a rate of 9.8 meters per second squared. So the question is, where does the hunter want to aim to hit the monkey? Does he want to aim directly where the monkey is right now? Make that a little straighter. Does he want to aim directly where the monkey is right now? Does he want to aim below where the monkey is right now, so he can hit him on the way down? Or should he aim above where the monkey is right now? Above where the monkey is right now, because his bullet is going to be fired as a projectile, and the projectile is going to curve down. So we've got three options. Aim above the monkey, aim at the monkey, or aim below the monkey. If you want to hit the monkey with your tranquilizer dart, do you want to aim above, at, or below, assuming that the monkey is going to start falling the instant you pull the trigger? So I have neither a monkey nor a gun here, so I'm not going to be able to do this demonstration. So again, we are going to rely on the good people who post to YouTube. In this case, MIT's demonstration department put the shooting the monkey demonstration together. We're going to link to that, which should be right here-ish, assuming I can figure out how to set links up. So what we're going to do again, go over to that video, watch the shooting the monkey video, and then we'll go over the reasoning behind how it works and do the math behind it right here. So pause here. So from the video, you should have seen that the hunter was aiming directly at the monkey, or at least the demonstration hunter was aiming directly at the monkey. So why do you want to aim at the monkey rather than below the monkey if we want to hit the monkey? Why is that? To help illustrate this, I'm going to do a thought experiment here. Let's imagine we could flip a switch and just turn off gravity. So gravity which normally would have pulled the monkey down. The monkey's not going to go down. The monkey's just going to stay in the same spot. And gravity, which would normally have pulled the bullet down as well, we're also going to turn that off too. So we're just turning off all gravity. So the bullet now, instead of undergoing a parabolic trajectory where it's curved, it's just going to go in a straight line toward the monkey. So in this instance, when there's no gravity, you would have to aim at the monkey, directly at the monkey, because nothing's going to curve the motion of the bullet. The monkey's not going to move. You're just going to aim directly at the monkey. So if we have no g, I'm going to write this as the height of the bullet with no g, with no gravitational, with no gravity on. At the moment of impact, these two things are going to be equal. The height of the monkey with no gravity is going to be equal to the height of the bullet at no gravity. This is at the moment of impact between the bullet and the monkey. Okay. Well, what's the only difference between these equations if we turn gravity on? If we turn gravity on and you look at your kinematic equations, the only difference is that with gravity, the height of the bullet is going to be altered. So this is relative to no gravity. All we have to do to get the height with gravity is just subtract 1/2 gt squared. It's the only extra term that shows up when I add gravity is just that the g is not 0. Same thing on this side. The height of the monkey with no g is just the same thing minus 1/2 gt squared. Gravity pulls all objects down at the same rate. So if these two things were equal before, when there was no gravity, they're still the height with gravity, so this would be the height of the bullet at the moment of impact with gravity, and this would be the height of the monkey. It's the same thing as the height of the monkey without gravity, except now I put the gravity in. However, these two things have to be equal because I've changed them by the same amount. I've changed both of them by 1/2 gt squared. And if I've changed both of them by the same amount, they still have to be equal. Okay? So this is why you want to aim at the monkey. Because gravity works the same for the bullet. It's going to make the bullet curve down, and it's going to affect the height of the bullet just as much as it affects the height of the monkey. Now we are going to consider something called the range equation, which essentially is an equation that will tell us if I'm firing a projectile from a cannon, here's my cannonball, and it's going to land right here, what is the range R that the projectile is going to travel? So my projectile goes up and comes down. To solve this projectile motion problem, we are going to follow the same steps that we did before. Namely, we're going to define our coordinate system, break all of our vectors into their individual x and y components, and then solve the one-dimensional motion equations that we have dealt with many times before. So let's see how we can solve this range equation. I've already drawn in my coordinate axes. I've defined the origin to be the spot where the cannonball that I am firing leaves from. So I've defined my coordinate axis. So we should be good with step 1. Step 2 is we want to break all our vectors into their different components. Now I have two vectors that I'm going to be working with here. I have my initial velocity vector, this should really have an I on it, and I have my gravitational vector. Now the gravitational acceleration vector, The gravitational acceleration vector looks like this. It's easy to write down because it has no value in the x direction, but it has a value of negative 9.8 meters per second squared in the y direction. However, to get the initial velocity x and y components, I have to do a bit more work. I'm going to redraw my initial velocity over here. Here's VI. And I want to break that vector. I want to break it up into its individual x and y components. To do that, I will make note of the fact that the projectile leaves at an angle theta, as I've defined up here, so that if I look at this side of the vector, that's the y component of the initial velocity, and I also have the x component of the initial velocity. And we've done SOHCAHTOA on these triangles many times now. So by this point, hopefully you know, or at least can figure out, that the x component is just going to be given by the magnitude of the initial velocity times the cosine of theta. And the y component is going to be given by, again, the magnitude of the initial velocity, that's just equal to the speed, times the sine of the angle between them, so that I can write down that my initial velocity has an x component, which is going to be VI cosine theta, and a y component that is going to be VI times the sine of theta. So we've done step 2. We've taken the two vectors in the problem and broken them up into their individual x and y components. So we have our two components. We have the g acceleration of gravity, which is negative 9.8 meters per second squared in the y direction. And then I have the two components of the initial velocity vector. So for example, if I were giving you a problem, I might tell you that the initial velocity was 30 meters per second. And I might tell you that theta was 30 degrees. It doesn't have to be 30 and 30. I could choose any numbers I want for the initial launch angle and the initial speed of the projectile. But we want to figure out how far that projectile is going to go. And to do that, I need to solve for both the motion in the x direction and motion in the y direction. Now it's obvious why I have to look at motion in the x direction. I want to find the range. The range happens to be in the x direction, so I have to pay attention to that. Why do I have to pay attention to the motion in the y direction? Well, motion in the y direction tells me when I'm going to hit the ground. So we start, assuming the cannonball starts at the back of my cannon over here, we start at a height of y is 0. Once the cannon is fired, though, the cannonball goes up and comes down, which means it finishes at a height y equals 0. So the time at which the final height is 0 is going to tell me how far the cannonball has traveled. Okay, so there's two times where we are going to get a solution where the height is 0, initially at time 0, and then again at some other time over here. And I need to use that information to figure out when the cannon has reached the ground. Okay. So we're going to use that time later. So I want to look at this equation, this kinematic equation, and solve for the time. But let's see what's going into that kinematic equation. I've got my initial y height. Well, we've just said that that's going to be 0, because we're starting on the ground. We've got our final y height, which is also going to be 0, because we're interested in the time when the cannonball hits the ground. Then we have our acceleration, which was negative 9.8 meters per second squared. I'll call that negative of the magnitude of the acceleration of gravity. Put that in absolute value. It's there. Then I have the initial velocity in the y direction, which I can just read off from over here, because we've solved for that. We solved for that when we found the components in the y direction. So that would be v initial times the sine of theta. In the initial problem, we've given you the initial speed, or initial magnitude of the velocity, and the angle. So I can solve this equation for the one thing I have left, which is time. When I do that, you're going to get two solutions, because it's a quadratic equation. One solution, when you factor it out, you'll find that you get a height of 0 at time 0, which of course has to be true, because at time 0 we started on the ground, so that's a height of 0. But then the other t, actually let me go through and solve it here. So if I plug in numbers here, you'll get 0 equals v sine theta times t minus 1/2 absolute value gt squared. So if we factor out 1t, that's how we get the t equals 0 solution. So let's factor out that t. So just divide through by t, and we're left with 0 equals v sine theta minus 1/2 magnitude of g times t. I solve for that t by moving the 1/2 gt to the other side and dividing through by 1/2 g, and you get that t equals g, magnitude, let me do this correctly, 2 times the magnitude of g, nope, sorry, still wrong. 2 times the v sine theta divided by the magnitude of g. Let me just check my notes to make sure that's correct. It is. And since it's correct, I put a little box around it. So I know this is how much time it takes to hit the ground. Now, if you're worried about doing your algebra correctly, I know I stumbled a little bit, we can always just check that the units are working out correctly through dimensional analysis. I have v, which is in meters per second, divided by g, which is in meters per second squared. When I divide by meters per second squared, all I'm doing is I'm flipping the fraction. So I'm getting seconds squared over meters, which when you multiply by meters per second will just give you seconds, which is the unit we want since we're looking for time. By looking at motion in the y direction, we have figured out the time it's going to take the projectile to come up and then come back down and hit the ground. So that time is going to occur right here, right when the projectile is hitting the ground. Now that I know that time, I'm free to find the distance in the projectile has traveled in the x direction. So we've looked at the y direction, now we're going to look at the x direction motion. And I'm just, again, going to look at one of my kinematic equations. So I look here, and I say, well, what's my initial x position? Well, we define that based on our coordinate system to be 0. My x velocity was just given by the velocity vector that I found before by breaking my velocity into components. That was vi times the cosine of theta, my initial speed times the cosine theta. Now we have this ax here. Now there's going to be a big temptation to say that the acceleration of a projectile is 9.8 meters per second squared. And it is, but that's not the acceleration in the x direction. Remember, we wrote down what the acceleration was in the x direction. And the acceleration in the x direction was 0. Gravity doesn't pull you in the x direction. It was negative 9.8 meters per second squared in the y direction, but that we just wrote as minus g. we're not in the y direction anymore. We've got a 0 acceleration here. So everything in there is just 0. That works out very nicely, because the only thing that I have left are x final, which just tells me the range that I've traveled, that's what I want, and t. And t we solved for from the y, the motion in the y direction. That was just 2 times the initial velocity times the sine of theta divided by the magnitude of g. So let's write that all out. When we finally solve for the range, that will give us, let's see, that's 2 vi squared, because I have a vi from the t and a vi from the initial velocity, times sine theta times cosine theta divided by the magnitude of g. Now it turns out, if you remember your trigonometric identities, there is another way of writing this range equation, because there is an identity that says 2 sine theta cosine theta is exactly the same thing as the sine of 2 times theta. So we can rewrite our range equation in this way. This will be the easier way to write it. The range of a projectile is vi squared divided by the magnitude of g times the sine of 2 theta. Now let's see what happens as I change different parameters in my equation. So we always want to make sure what the, try this again, try it again. We want to make sure that our equation makes sense, both mathematically and physically. So let's test it mathematically first. So we look here. I want something that has units of meters, which means I better have units of meters on both sides of the equation. Let's see. So I have sine of 2 theta. That doesn't have any units, so I'm not going to worry about that. But velocity and acceleration do have units, so let's consider that. We have initial velocity squared. So that's like meters per second for the velocity, and then square the whole thing. So you get meters squared over seconds squared. And you're dividing by acceleration, which is meters per second squared. And when I take meters squared over seconds squared and divide by 1 meters and 2 seconds in the denominator, you are left with meters. So the units work out right. That's good so far. Next, we want to see, does the equation make logical sense? Does it make physical sense? Let's consider changing some of the variables on the right side and see what it does to the range. Let's say I make the initial velocity bigger. I fire a projectile with more velocity. Therefore, I would expect the range to get bigger as well. And if I plug in a bigger number for vi, it must be true that a bigger initial velocity gives me a bigger range. So that works very well. Now, let's say we could tune the acceleration of gravity. Maybe we go to a bigger planet, or the sun, where gravity is bigger, or we go to the moon, where gravity is small. What's going to happen to the range if I go to the moon? Right? We go to the moon, and the magnitude of g is smaller on the moon than it is on the Earth. Well, if I plug in a smaller number for g, smaller gravity, that means I'm plugging a smaller number in the denominator, which is going to give a bigger number on the right-hand side, which means we get more range. And that makes sense. on the moon, if you throw an object, it's going to go further because gravity is not pulling it to the Earth with the same acceleration. There's a nice video online of one of the astronauts swinging a golf club and hitting a golf ball. And in the words of the astronaut, the ball went for miles and miles. And you can see it just taking off and going a very, very long distance, even though he was in this big, bulky astronaut suit and couldn't very well swing the club. But that's exactly what should happen. If you take away gravity, the range is going to be larger. We could also plug in some numbers for theta here. What happens if I plug in theta is 0? So I fire it with just straight horizontally. Well, it's not going to make it all very far. It's going to hit the ground immediately. If you plug in the sign of 0, you will get a range of 0, which makes sense. It's going to hit the ground right away. Similarly, if I plug in the sign of 90 degrees, that would be like firing a projectile straight up. And the range of the projectile, even if it goes very high, it's not going very far in the x direction. If I plug in 90 for theta, I'm going to get the sign of 2 times 90, which is the sign of 180, which is also 0. Which makes sense because, again, if you fire a ball straight up, it's not going anywhere in the x direction. What's the best angle? Oops. The best angle to fire a projectile at if I want the projectile to go a large distance? Well, I want to make the sign as big as it can possibly be. And to do that, we want a sign of 90 degrees, which means we want an angle of 45 degrees. Which will give us the maximum range that we can fire the projectile. So if we go to 45 degrees, we're going to fire this is in the absence of air resistance. With air resistance, there are other forces that make it a bit more complicated. But in the absence of air resistance, we can see clearly from this equation that a 45-degree angle is the best angle to fire at because that gives us the biggest possible value for the sign in the